Hello everyone, my name is Karen Wolf and I'm what's called an academic development practitioner. What that means in our South African context is that I work with academics, and in my case that's engineering in particular. And my role is to support their development, help them to identify challenges in their curriculum and pedagogy, support the implementation of new strategies in teaching, learning and assessment, and collaborate on researching these initiatives. Now, the legitimation code theory dimensions have been extremely useful in my work across a number of sites. What I'm going to be doing in this video is sharing the work by some of my colleagues in the Faculty of Engineering at Stellenbosch University. A common industry complaint is that graduates do not know how to apply their theory in practice. So how do we, as engineering educators, address this challenge? How do we enable our students to leap into the real world armed with the knowledge, skills, practices and dispositions necessary to tackle 21st century challenges? Stellenbosch University is a contact-based residential research-intensive institution in South Africa. And although our engineering faculty draws the top students from around the country and beyond, we face similar challenges to engineering schools from the global south: large classes, resource constraints, and the urgent necessity to enable theory-practice bridging. A key instrument that has helped us to address enabling our students to apply their theory in practice is legitimation code theory semantics. Semantics has been used in our faculty since 2016, not only in individual subject areas, but as a way to view entire programs and staff academic development. Now, for those of you not familiar with semantics, this is a legitimation code theory dimension which helps us to see the relationships between theory and practice, between concepts and contexts. By proactively enabling students to connect theory to practice in a cumulative manner, we can effectively wave through a class or curriculum, connecting the dots between why, what and how in the context of who, where and when. Our National Council on Higher Education has recommended 4 fundamental curriculum principles: foundation provision, the recognition that serious knowledge gaps need to be filled given problematic curricular assumptions about students' prior knowledge; epistemic transitions, the need to explicitly scaffold students' epistemic development beyond foundation provision; curriculum enrichment through key literacies; and curriculum enhancement through greater breadth of exposure in order to produce employable graduates for the contemporary world. Using semantics, we can arrange these principles across a program, from the more conceptual or context-independent foundations through to more concrete, context-dependent, real-world practices. Using this framework, we're going to demonstrate how different academics apply cumulative learning principles in their subject areas using semantics, and how these are collectively used to support academic staff development.
We set up the test to help students to go through a learning process, to practice how to do unit conversions. And we also wanted to instill in students a sense of how important unit conversions actually are.
Our first case study is a first-year chemistry course for all engineering disciplines with around 1,000 students. There isn't time to revise the chemistry fundamentals, so a group of lecturers has developed a randomized online quiz bank. The activity was designed to be a low-stakes formative assessment, allowing the students to retake the tests in order to improve their marks and, of course, to learn. Questions in the database are designed to allow the students to surf down the wave, pulling through the conceptual through to the contextual through a set of progressive questions. Questions range from pure science, foundational, conceptual, or theory-based questions that may be somewhat abstract to the student, and move into the application of theoretical concepts in scenarios where there's a clear formulaic or mathematical procedure that can be applied. Finally, the students move to questions with less clearly defined answers, but that are contextually familiar to them, where they would be required to use some sort of engineering judgment.
We're referring to, for example, a grasp of different concepts such as physics concepts or chemistry concepts. And what you can see here is some of the classifications. So principle of convention, significant figures, which is something that's also very important within our course. Some of the questions were plain arithmetic questions, which you didn't have to understand the context of the question, you just needed to understand the maths. And then some questions, especially on the estimation side, were questions that related to everyday things which students could understand. And we noticed that there were some questions in the question bank which students coming from certain contexts wouldn't be able to formulate a solution strategy for because they have no context of what the question is. So for example, if you ask a student to estimate the number of ping pong balls in a swimming pool, in an Olympic swimming pool, if a student doesn't know how big an Olympic sized swimming pool is, it becomes difficult to answer that particular question.
The first step is to, when we cast the foundational theory, we start off with a textbook. Now, a typical textbook image is the one I've shown you here from Aker et al. 2017. Now, for anyone with any kind of technical background, you won't immediately understand what motion is being indicated in this image. This is a Chebyshev, a very simple four-bar mechanism. But it's very difficult to understand how the point P stays horizontal. And the best way to do this is to go a step higher and introduce some visual confirmation of what's happening. Now you can see why P stays on a horizontal line. You can also see how C and B are also moving in relation to the textbook image. From this, you can also see, okay, now I know where my single degree of freedom joints is, and I can also count them because it's so easy to see from these GIFs, and I highly recommend GIFs. So the other thing that you can do to get the students to, sort of a very hands-on approach is for them to engage with the mechanisms themselves in and around their house. Now, obviously, a very cool idea is to physically print your modules using a 3D printer, but not everybody has access to that. So what I did was I showed them how to build their own simple mechanism just using whatever they have found around their house. You can see how simple it is. I mean, anybody with a pair of scissors and some foam can build this. People use cardboard, paper, whatever. So now you can see, all right, that's how it moves. And now we can do a little bit of maths on that. And we can easily calculate what our number of bars are because you had to cut them out yourself. There were 4. How many single degree of freedom joints you have? Well, I used 4 pins, so that's 4 as well. We have no second degree of freedom joints. And so it just becomes a bit more, okay, I need to figure out how this works for myself using, the hands-on technique. And it's a very cheap way to do it.
In our second case study, we start at the bottom of the wave with a flipped classroom case study assignment for a second-year material science course for mechanical, mechatronic, and industrial engineering students. The challenge in the syllabus is to avoid siloed learning in the face of the broad and dense syllabus. Lecturers use a case study of failure analysis in order to pull various theoretical concepts and procedural analysis techniques together in a real-world application. Again, this is designed as a low-stakes assessment in the form of a reading assignment, a walkthrough video that directs students back to the textbook chapters to help them connect the dots, and a multiple attempts online comprehension quiz with formative feedback between the attempts in order for students to check that they are getting it. The student is taken on a job shadow journey with a consulting engineer, climbing back up the wave by starting with a contextual real-world engineering problem. A vehicle wheel axis has failed and you as an engineer need to determine why. Various material and mechanical tests are used in order to determine the material and mechanical properties of the axle, and then the properties are linked back to the expected behavior from a theoretical perspective. The student is then guided into interpreting the results in order to determine the reason for failure.
Okay, so what we did, it was a learning opportunity in Chemical Engineering 264, Fluid Mechanics for the second year Chemical Engineering group. Each student was asked to choose an application of fluid mechanics, whether that be in industry, in sport, nature medicine, etc. And then each student had to present in a video format, focusing on describing the application and the specific fluid mechanics fundamentals that are at work in the application chosen. Each video was simply a slideshow with a voice recording, and the video lengths were limited to 5 minutes. Each student could use software of their choice to create and edit the videos, although a Microsoft PowerPoint tutorial was provided. The videos were distributed among students within small groups of about 5, and each student's video was viewed and assessed by the 4 peers in their group, as well as one of the module instructors. One of the things that worked very well was giving the students the opportunity to choose their own topic or application. Initially, we asked the students to give 3 potential topics, and we chose the topic that they should focus on, so as to minimize duplicate topics later on when they were divided into groups. By giving the students a choice, we increased the buy-in from their side, because then they would be talking in their presentations about things that they were interested in, and we could also keep the scope or the fields open to allow them to choose any application from any area that they liked, instead of just the typical industry related examples that they find in the textbooks. So the idea was to get them to start seeing the normal world around them through the eyes of fluid mechanics. And then in the small groups as well, we tried to vary the themes or the fields as much as possible so that each student could be exposed to applications from different contexts. So essentially asking the students themselves to find extra examples to supplement what they see in the textbooks.
Now we look at moving up and down the wave, integrating concepts and applications and contextual situations. In this case study, a third-year transport engineering course for civil engineers is used. Students are assigned a road design project where they work in small groups to find an appropriate local site where they can apply road elevation concepts to create a particular road design. This case study is designed to use elements of experiential learning, peer engagement, and teamwork to simulate a real-world engineering application, including tasking them with the use of software and translating technical information into a readable report. The students snakeboard up and down the wave to integrate the know, be, do elements of learning engineering. They start with the conceptual and look for a contextual scenario where the concepts can be applied. Then they apply the analysis and design principles and procedures to create their solution, and integrate these elements into a final design report where they have to use the road design software.
So here, going back to chemical engineering, we look at a 4th year subject that they have. In their final year, my colleague Professor Christy Dorflin integrated a week-long series of site visits to mining and metallurgy plants in Gauteng, so that those students' final year projects could more explicitly link theory to practice in a complex context. So building on this initial part of the wave, this initial lecture, tutorial, practical, semantic wave, the site visit then enables the student not only to link those concepts, and this understanding was revealed in improved assessment performance, but also to develop a better grasp of what happens in actual practice. Students commented on learning about the health and safety of chemical and engineering operations, about process economics, the scale of technologies, and the interesting relationships between different operators, technicians, engineers, managers in those spaces.
Mika and I recently undertook a study surveying first and then interviewing the last decade of alumni from the process engineering department. The purpose of the survey was to give our alumni a voice in helping us conceptualize recurriculation efforts. They obviously have an excellent insight into what skills, practices, and approaches are most useful in the world of work, seeing as that they have made that transition and are currently working for the most part. Essentially, the project allows for insights into the completely contextual positioning of the full curriculum. Alumni gave feedback on day-to-day operations, which skills they used most frequently, and skills they are not sufficiently covered in the curriculum, in their opinion, and what has been well covered. Feedback was overwhelmingly positive, with most alumni very grateful for the strong foundation in particularly technical engineering content. However, there was a strong recommendation for grounding theoretical work in actual industrial experience, which can be difficult in a university context. Many alumni recommended a closer tie between the very theoretical courses which we teach and the application-driven use of the technical content in industrial spaces, although this depends on the kind of industrial spaces that they're in.
If you look at the top 5 or 6 skills or types of work that people are doing, it's lots of interpersonal stuff, collaborating with team members, technical writing, analysis of systems, yeah, that's a nice technical one, project management, management of finance and economic decisions, staff or team management, stakeholder engagement. These are all things that are as part of a hidden curriculum in our undergraduate, perhaps aside from project management is explicit and report writing, which we do significant time on. But we don't have anything on, well, how do you engage with subordinates? If you have to collaborate with team members, we do lots of teamwork and our undergraduate students hate it. They complain about it all the time, but this is then the top thing that you do. This is basically you do every day. And it's a set of skills that perhaps we need to be focusing more on.
Looking through the lens of LCT, we can consider the feedback at 3 levels of semantics, semantic gravity, and inform our recurriculation efforts accordingly. At the most reified level, the curriculum must be positioned within X's framework, an overarching positioning of the degree within the larger engineering community. A focus on the broadest skills, the core concepts in engineering, and the requirements for professionalization of the field. At the mid-level, moving towards application, the pedagogical focus examines specific skills in, for instance, mathematical sciences, scientific literacy, investigation, experimentation, and most importantly, design. This is a strong focus of the current curriculum. Theorized and exemplified, the content of the curriculum covers content in a strongly theoretical positioning. However, the alumni particularly argue for increased emphasis on the contextual focus at the lowest or the most grounded level here, linking concepts through application to contexts such as actual industrial experience. We can weave this contextual positioning all the way up the wave without losing the keen edge of technical know-how which our students master through creative and interesting application-driven content in our theoretical courses.
So each of these case studies illustrate how the engineering educators themselves are bridging theory and practice divides in their subject areas. But each of these case studies is also supported by a particular educational theory, such as unpacking threshold concepts to support epistemic access, or self-regulated learning through the flipped classroom approach, or using pedagogies of engagement and experiential learning to build professional identity. If we look at these initiatives collectively, we can see that they too can be located on the semantic wave. They demonstrate the active bridging of educational theory and practice in the engineering education context. They provide examples of contextualization of the scholarship of teaching and learning, and through sharing these examples with their peers over a variety of platforms, they enable epistemic access and cumulative learning, from core pedagogical concepts through applied classroom initiatives into contextual applications of learning opportunities across all the engineering disciplines. Ultimately, they supported the establishment of a sustained community of practice. We can see that this project has enabled reflective teachers to develop a scholarly approach to their teaching, while enacting the institutional vision of creating an engaging learning environment that supports student success.
Although many of these initiatives have been written up and published in formal journals and conference proceedings, practical accessibility is a very important feature of our approach. Most of the initiatives have been captured over the past few years as posters or case study videos. Now, these resources are available on a dedicated shared faculty website. Collectively, they represent practice-based examples of engineering education strategies underpinned by educational theories, and they're created by engineering academics themselves for engineering academics in our Global South context. The case studies and initiatives are supported through teaching and learning mentorship and funding for things like student assistance, equipment, and other resources. The faculty hosts annual workshops, teaching mornings, and a teaching forum where these case studies are shared and developed. Staff feedback indicates that exposure to the educational theories has enriched their practice. They speak of engaging with accessible methods and tools to understand student learning, and explicitly refer to the collaborative community of practice approach as supporting the development of their scholarship of teaching and learning. We believe that such a developmental community of practice approach enables engineering academics to take ownership of their teaching roles and to strengthen their sense of identity and belonging in their profession. And isn't this exactly what we want for our students and graduates? The ability to effectively draw on their professional knowledge in practice.